So, welcome to this our continuing series of lectures on transport processes. In the last lecture, I had derived for you the conservation equations in vector notation for mass, momentum and energy conservation. All these conservation equations have a common form. For the concentration field, for example, dC by dt plus u dot grad c. This is only for incompressible flows where the divergence of the velocity is equal to 0. Okay. It's equal to d del square c. And if I scale, okay, c is equal to c minus c infinity. Where I have, for example, in the case of internal flows, I have velocity u and a characteristic length d. For external flows, okay, this is d, the characteristic length, okay, and this is the velocity u. I will get an equation of the form the Peclet number times partial c by partial t and when the Peclet number is small compared to 1, this left side is small compared to the right side. Okay. This left side is small compared to the right side. Therefore, if I neglect convective effects and consider the transport to be diffusion dominated, the conservation equation becomes del square c equals 0 for the concentration field. Alternatively, del square t equals 0 for the temperature field. These are diffusion dominated transport problems. They reduce to solving a Laplacian operator equal to 0 subject to boundary conditions. Okay. So, we will look at how to solve equations of this kind for diffusion dominated transport. Now, let us take first a Cartesian coordinate system. So, that is the simplest coordinate system that one can envisage. Okay. X, y. The simplest problem that one can consider is, for example, in 2 dimensions, the transport in a square or a rectangular block. Okay. So, I have a rectangular block of a solid or a fluid which satisfies the conservation condition. Let us assume that the length in the x direction is Lx, the length in the y direction is Ly. Okay. And I will assume that the 4 faces are at different temperatures. Okay. The face at x is equal to 0 is at temperature T naught, at x is equal to Lx is at temperature T naught. So, therefore, these 2 faces are at constant temperature. The top and bottom faces are at some different temperatures. Okay. And I want to find out what is the temperature distribution throughout the system. Okay. Therefore, this is a diffusion dominated problem. I need to solve the equation del square T equals 0. In this particular case, I will first consider the system to be at steady state. Therefore, there are variations only in the x and the y directions. Okay. Partial square t by partial x square plus d square t by dy square. This is equal to 0 is the conservation equation. Okay. And the boundary conditions t equals T naught at x equals 0, call this as T b. Okay, so, those are the boundary conditions that I need to solve the problem with. And whenever you have differential equations of this kind, the natural procedure to use is the separation of variables procedure. However, as I had repeatedly emphasized when we were solving different separation of variables problems, it is necessary in a separation of variables procedure to ensure that there is homogeneous boundary condition in all directions except one. Homogeneous boundary condition means either the temperature is 0 or the derivative of temperature is 0 or some combination thereof is 0. Okay, so, those are homogeneous boundary conditions. In this particular case, I can ensure that the temperature is 0 on the surfaces at x is equal to 0 and at x is equal to Lx. Okay. I can do that just by writing T star is equal to T minus T naught. Okay, so, if I just write T star is equal to T minus T naught, okay, I will ensure that T star is equal to 0 at x is equal to 0 and T star is equal to 0 at x is equal to Lx. Okay. The inhomogeneous direction then becomes the y direction. Okay. T star is equal to Tb minus T naught at y is equal to 0 and T star is equal to Ta minus T naught at y is equal to Ly. Okay. So, that becomes the homogeneous inhomogeneous direction. So, I have homogeneous boundary conditions along the x coordinate and the inhomogeneous driving is along the y direction, okay, because I have non-zero temperature boundary conditions at y is equal to 0 and y is equal to L. Okay. So, now I have made one direction homogeneous and therefore, I can go ahead and try to solve the problem. Okay. So, the first thing I have to write t is equal to some function of x times some function of y. Okay. Insert that into the equation. Okay. Insert that into the conservation equation. Okay. So, I will get x times partials equals 0 and I divide throughout by x times y. Okay, divide throughout by x times y, in which case I will get 1 over x d square capital X by dx square plus 1 over y. Okay. So, I substitute temperature is some function of x times some function of y, insert into the equation, divide throughout by x times y. Once you do that, you have now one term which is only a function of y and the other term which is only a function of x. Okay. Therefore, both of these terms have to be equal to constants. Okay. They have to be constants of opposite sign, so that they can add up to 0. Okay. In this case, they have to be constants of opposite sign, so that the sum of these two is equal to 0. Okay. Now, what constants should they be? Okay. Should they be positive or negative? Obviously, if one is positive, the other has to be negative. Okay. How do you decide which one to choose? Okay. That decision depends upon the boundary condition, which is the homogeneous direction. Okay. Okay. I have one variation in x and the other variation in y. Okay. I have a homogeneous boundary condition at x is equal to 0 and x is equal to Lx. Okay. Therefore, I would expect that in the homogeneous direction, I should have sine and cosine functions, so that I can satisfy the boundary conditions in the x direction, the homogeneous boundary conditions. Okay. As you can see, the solutions of this. Okay. So, if I take the solution of this equation, this is a total derivative because x is only a function of x. Okay. There are two possibilities. One is if it is positive, okay, in which case x will be equal to a e power some constant x plus b e power minus alpha x. Okay. A second order term equation which is positive, the square root of these. So, this will be of the form this is equal to alpha square, a positive number. The solutions will be exponentials. Okay. These exponentials do not pass through 0. Okay. E power plus x is 1 at 0 and it goes to infinity. E power minus x is 1 at x equals 0, it goes to 0 as x increases. Okay. These are monotonic functions. Okay. Therefore, if I were to impose x is equal to 0 at x is equal to 0 and at x is equal to Lx, okay, the only solutions that I will get will be a equals 0 and b equals 0. Okay. So, in the homogeneous direction, if I assume a positive constant, the solutions are exponentially increasing and decreasing functions, and you cannot impose homogeneous boundary conditions. The only solution is for both a equals 0 and b equals 0. Okay. We have seen that when we did the unsteady problems. Okay. Therefore, this does not give you solutions that decrease to 0 at both boundaries. Okay. Therefore, the only solution, okay, that I can get which will decrease to 0 at both the boundaries is if this constant is negative. Okay. Minus alpha square. Okay. In this case, if I solve this, I will get x is equal to a sin alpha x plus b cos alpha x. The requirement that x is equal to 0 at x equals 0. Okay. The first boundary condition here. Okay. T star is equal to 0 at x is equal to 0 will give me that b equals 0. Okay. I also have x is equal to 0 at x is equal to Lx. Okay. And that gives me a value of alpha. Okay, because I have these solutions are in the form of sine functions. Okay. These solutions are in the form of sine functions. Okay. Okay. Therefore, alpha has to have specific values so that the value of x becomes 0 at small x is equal to Lx. Okay. So, the solution for that is that alpha is equal to n pi by Lx. Okay. You can see that when alpha is equal to n pi by Lx, when x is equal to Lx here, okay, when alpha is equal to n pi by Lx, you have sine of n pi and that is 0. Okay. So, therefore, this is a valid solution, okay, a sine function. It decreases to 0 on both the left and the right faces. Okay. So, it satisfies both boundary conditions, okay, where n has to be an integer. Okay. Therefore, the solution for this is that x is equal to a sin n pi x by Lx, okay, and alpha is equal to n pi by Lx. Okay. So, we have got the form of the solution in the homogeneous direction. These are in the form of eigenfunctions. As I told you earlier, these eigenfunctions are the natural solutions in a Cartesian coordinate system, the sine functions. They satisfy the boundary conditions of 0 temperature or 0 concentration on 2 fixed surfaces. So, they are the natural basis set which can be used for expanding these functions. Okay. And since the Laplacian, so since the operator, okay, is the same, okay, the operator, the diffusion operator is a second derivative. Therefore, you will always get these sine functions as solutions. Okay. Okay. So, therefore, I have solved 1 over x d square x by dx square is equal to minus, okay, n pi by Lx the whole square, okay, minus n pi by L x whole square, which means that the y derivative has to be of opposite sign. Okay. That means that the y derivative has to be of opposite sign, okay. Because the x term plus the y term, they have to sum to 0. Therefore, the y term has to be of opposite sign. Okay. Therefore, the equation for y will be of the form 1 by y d square y by dy square is equal to plus n pi by L x the whole square. Okay. So, that it satisfies the conservation equation that the sum of these two terms has to be equal to 0. Okay. Recall that the y direction is the inhomogeneous direction. Okay. Recall that the y direction is the inhomogeneous direction. Okay. This can now be easily solved. Okay. Y is equal to a exponential of n pi y by L x plus b exponential of minus n pi y by L x. Okay, so, those are the two exponential solutions in the y direction. Okay. So, a general solution for this, okay, will be, okay, that the temperature, okay, is equal to a exponent of n pi y by L x plus b exponent, okay, of minus n pi y by L x. Okay. This whole thing, this is capital Y, this has to be multiplied by x. Okay. Therefore, I have to multiply this by sine of n pi x by L x. Okay. So, this is the solution. This solution satisfies the equation. You can easily substitute that into the equation and see. This solution satisfies the equation and it satisfies the homogeneous boundary conditions in the x direction. It satisfies those for any value of n. So, the most general solution is the summation n is equal to 1 to infinity of a n plus b n. Okay. This is the most general solution, okay, because this the product of these two terms, the y as well as the x, satisfies the equation for any value of n. So, the most general solution is when you multiply these two and you can sum up the series from n is equal to 1 to infinity. So, this satisfies the equation, it satisfies the homogeneous boundary conditions. It does not yet satisfy the inhomogeneous boundary conditions. How do we satisfy the inhomogeneous boundary conditions? As usual, we do it using the orthogonality relations. So, let us do that. So, the solution that I had for the temperature field, summation n is equal to 1 to infinity, okay, a n e power n pi y by L x plus b n e power minus n pi y by L x into sine of n pi x by L x. Okay. And the inhomogeneous boundary conditions are that at y is equal to 0, right, T star is equal to T b minus T naught. Okay. Recall that at y is equal to 0, the value of T star is equal to T b minus T naught. Okay. Yeah. Okay. So, that was the boundary condition, okay, which implies that T b minus T naught is equal to sigma n is equal to 1 to infinity of a n plus b n sine okay. So, that is the equation, and now I need to get an equation for a n and b n, okay, And how do I do that? I use the orthogonality relation, okay. Integral dx, okay, from 0 to Lx, okay, sine of n pi x by Lx we had previously expressed it in terms of x star. So, x was basically 1 over Lx. Okay. In this case, since the length in the two directions are different, I have left it as length itself. Okay. So that is a slight simplification, but nevertheless you can do this integration, and this will just give you Lx by 2 times delta mn. Okay. So, this is non-zero only when m is equal to n, and when m is equal to n, this is equal to Lx by 2. Okay. So, what do? Multiply both sides of this equation by sine of n pi x by Lx and integrate. On the left side you can do the integration. Okay. This will be equal to Tb minus T naught, okay, into, okay, 2 Lx by m pi. Okay. Let me just confirm that for you. Yeah, 2 Lx by m pi. Okay. And this is 2 Lx by m pi for odd m, and it is equal to 0 for even m. Okay. So, you can actually write it simply as so, this factor here 1 minus 1 to the power of m. Okay. If m is odd, this is equal to 2. If m is even, this is equal to 0. Okay. So, this integral is non-zero only for odd m and is equal to 0 for even m. Okay. So, that is the value of the integral, and on the right side I have a n plus b n, okay, into Lx by 2 delta m n. Okay. And this is of course non-zero only when n is equal to m. The right side is non-zero only when n is equal to m. Okay. Therefore, I can write this effectively as a m plus b m into Lx by 2. Okay. And this can now be solved. Okay. Therefore, a m plus b m is equal to Tb minus T naught into 1 minus 1 power m. Okay. The Lx will cancel out on both sides. I will get a factor of 2 here divided by m pi. So, I have got one equation that involves a n and b n. Okay. I have a m plus b m is equal to T b minus T naught into 2 into 1 minus 1 power m, okay, by m pi. This was from the boundary condition T star is equal to T b minus T naught at, okay, y equals 0. Okay. I have one more boundary condition, the boundary condition at y is equal to Ly. Okay. Okay. So, I have to impose this boundary condition at y is equal to Ly. Okay. The same boundary condition at y is equal to Ly, and if I do that, what I will get is T A minus T naught is equal to summation n is equal to 1 to infinity, okay, into A n times e power, okay, n pi L y by L x, because this is at y is equal to L y. So, instead of y I have to substitute L y, okay, plus B n e power minus n pi L y by L x into sine n pi x by L x. And now once again I have to substitute in terms, I have to use the orthogonality relations for the, this is the boundary condition that T star is equal to T A minus T naught at y is equal to L y. Okay. So, this is the second boundary condition. So, once again I have to use the orthogonality relations, okay. Integral dx T A minus T naught, okay, sine m pi x by L x, okay, 0 to L x is equal to summation n is equal to 1 to infinity A n e power n pi L y by L x plus B n okay, this whole thing into integral 0 to L x dx sine and you can simplify this, and what you will end up with is on the left side, okay, you will get T A minus T naught, okay, into 1 minus 1 power m, okay, by m pi, okay, similar to what we had got previously, okay, similar to what we had got previously, okay, and I should put a factor of L x there, okay, when I do the integral. Okay. And here I will get A m e power m pi L y by L x plus B m e power minus m pi L y by L x into L x by 2. Okay. So, that is the equation that I get from the orthogonality relations by using the fact that this is non-zero only when n is equal to m. Okay. And with that I will get two simultaneous equations. Okay, I will get two simultaneous equations. The first one is of this. Okay, the first one is this one. Okay. So, if I write it once again. And the other one is at A m e power and these are two simultaneous equations that can be solved in order to calculate these constants A m and B m. Okay. Okay. The constants are a little complicated in form, so I will not go through the details, but you can solve these equations both simultaneously and determine what the two constants are. Okay. And once I have that, the temperature is just determined as summation n is equal to 1 to infinity of I am sorry. Okay. So, those are the solutions for this equation for this heat conduction problem, okay, in which I had a distance Lx in the x direction, a distance Ly in the y direction, okay, and this is y. And I had different temperatures on the four different phases T naught. Okay. So, that is the procedure for getting this solution for this separation of variables problem. Okay. I will continue a little bit, revise this once more, and then we will proceed to looking at separation of variables in a spherical coordinate system in the next lecture. I will see you then.